Okay, thank you very much, Danielle, and thank you to Iris for the invitation. This is a huge privilege. Seismic event location is something that I've been interested in for many different kinds of sources and different kinds of events. And on the screen in front, there are two images of two slightly different scenarios. And on the right is the North Korean nuclear test site, which has had a lot of attention recently. And to talk about what we can and maybe cannot say about locations of these nuclear explosions. And on the left is the aftershocks from the October 2005 Kashmir earthquake. And these are just two examples where I've been very interested in how better we can locate them than our models would suggest. When putting this talk together, I was absolutely shocked to find that the late Alan Douglas's paper, Joint Epicenter Determination, was 50 years old in the summer. And I just post a little clip of it on the right-hand side of the screen just to show you what a paper from Nature looked like 50 years ago. And it's a very, very simple paper, but it's of enormous importance. And the reason for that is that this paper is essentially telling us that we are aware that there's bias when we're trying to locate a seismic event using arrival times at different stations. But if we locate two or more events together, then the bias for any given station can be accounted for and accommodated. And this, in a sense, forms the basis for all of the methods we have for what I think of as contextual location. So we need three things essentially to locate seismic events. Number one is obviously the data, the waveforms and the arrival pics, etc. But secondly, we need a velocity model. And just going down on this list, I sort of show a history of the previous century of how our 1D dimensional layered velocity models of the Earth's structure improved. At the bottom in 1995, we come to this model called AK135, which is essentially still the benchmark model for the one-dimensional structure of the Earth. And I suspect that it's not actually going to be improved, because I think the biggest challenge is characterizing the three-dimensional structure. And of course, as a lot of deep Earth people will know that there are many different kinds of models for three-dimensional structure, but I list a couple here, just the ones that are well known in the nuclear explosion monitoring community: SALSA 3D, and the Lawrence Livermore 3D Earth model. And then what we call RSTT, regional seismic travel times, which is a sort of an approximation of a 3D model for regional travel times, which are usually the most problematic. So these improvements in velocity models go a long way to reduce uncertainty in event location. And of course, finally, there's the method that we apply. There are many sort of different procedures that we can apply in our algorithms for event location. For example, source station correction terms, which we can either impose if we know that the model to some station is deficient. A lot in microseismic and sort of smaller scale problems, we have very, very, very complicated velocity structures, for example, in mines or reservoir systems. And it's usually necessary to pre-calculate three-dimensional travel times, and then we can sort of do grid searches or migration to sort of do sort of brute force location of events. There's a family of differential methods, which includes double differences and to some extent the sort of joint epicenter determination kind of things. And at the top here, I've included what we call pattern recognition, or what I think of as stamp collecting, which is not sort of event location as such. But if you have a seismic event, for example, in a reservoir or a geothermal field, which is recorded by only one or two instruments, there's probably not enough information in your seismic data to be able to say it was at this location. But what might often happen is, even though we only have 2 or 3 seismograms, we can say, well, we don't know where it was, but we know that the waveforms are almost identical to this other event, which we have located well. And in this way, we can use characteristics of the seismograms to sort of locate them, just putting them in context. And finally, which is probably what I'll be talking most about, is this sort of probabilistic approach, which I think is one of the most promising approaches in modern seismology. One region of great interest to me, partly because of my location, is the European Arctic, and this is, and you see on this map, is the spreading mid-Atlantic ridge north of Jan Mayen and beyond Svalbard. My good friend Øyvind Engen did a fantastic study about 15 years ago, combining different kinds of geophysical data sets of gravity, electromagnetic, seismic, and so on, to try and get as accurate as possible a picture of the seismicity along here. But at the time he did it, he was considering only seismic events up to 1998. And so nearly all of the events you see on this map are recorded only teleseismically. Very sort of few regional arrivals. But in the time since 1998, there's been an enormous expansion of an improvement of the seismic network in this sort of sparse region. There's been upgrades to the stations on Svalbard and on the islands and in far north of Norway. And in Greenland, the GLISTEN, or Greenland Ice Sheet Monitoring Network, has resulted in a huge improvement in the quality and availability of data. And I was very curious to see how much we could improve the appearance of this, of how clustered the seismicity along the ridge is. Another big development since 1998 is the CTBTO network, the International Monitoring System. And this fantastic seismic network consists predominantly of seismic arrays, which give you better steering, better signal-to-noise ratio, etc. And I don't think there's a single part of the world which has sort of better azimuthal coverage from IMS seismic arrays than the mid-Atlantic ridge. And so I wanted to sort of combine these regional and these teleseismic readings to try and really nail down the locations of these events as well as we could. Here we see 3 different existing catalogues. On the first plot here, we see the catalogue from the International Seismological Centre, which is a sort of mother of bulletins, if you like. They take readings from all the data centers and put them together and make a sort of super event bulletin. On the second one is the reviewed event bulletin of the CTBTO. So this is different in that it only consists of phase readings from IMS seismic stations, and there are other provisos attached to whether an event is included in this list. Down here we see the NORSAR regional events solutions, and it's kind of a bit unfair in a sense. So it looks like that's the least favourable distribution, but we have to remember that this has taken over a period of 20 years, and the number of stations available for this bulletin has changed enormously since 1998. So the spread of epicenter estimates is actually as much to do with the time and the network on which the readings were made. And down in the far corner is what I wanted to add to this. I took thousands and thousands of readings from all of the stations I could get my hands on in this reading, and tried to locate them. And what I was hoping was, with this wealth of much more seismic readings, we would get much better distribution. And the sad truth is it isn't really much better. There's as much spread as we could see before. So along came this wonderful location routine from Lawrence Livermore called BaseLook. If you don't know it or use it, I really recommend having a look at it. And whereas most seismic location algorithms take one event and locate it, so event by event, BaseLook takes dozens or hundreds or even thousands of events and calculates a joint probability distribution for the locations and the origin times. But in addition, it actually seeks corrections at travel time predictions, in other words, deficiencies in the seismic model applied. If we go back to the solutions we saw on the previous slide, here I show two different colours. They're exactly the same events and exactly the same phase readings, but I've used two very slightly different seismic velocity models to locate these with. Both of them are applicable to the European Arctic in the sense the FESCAN or Fennoscandian model is based on mainland Scandinavia, and the BARI model is sort of optimized to minimize travel time residuals in the Barents Sea. And you see, for any one event, if you use the BARI model or the Fennoscandian model, the location estimate falls in a slightly different place, and which just sort of adds to the spread. And then when you run the BaseLook program, the results kind of astounded me in a way, not just because of the compactness of the solutions, but the fact that it didn't actually matter the exact form of the velocity model applied. The Fennoscandian and the BARI solutions fall almost at the same place. And the reason for this is because corrections to the travel times predicted by these velocity models are being calculated implicitly within the program. And to illustrate this, you become suspicious when you see such a great improvement. Thing, well, it's Bayesian, is it? Is it just putting events where it thinks they ought to be? But if we do a little experiment and take each one of these earthquakes and sort of origin, lat long, depth, and then just calculate the travel time according to the applied model out to the KBS station for the first P arrival, the colour of each of these symbols represents the residual. So if you have a blue symbol, it means that the arrival came a little bit earlier than you thought it would. And if it's red, it meant it came a bit later. And you see that for any different event, when we solve the earthquake location problem event by event, there's a huge variation in this residual for this particular phase, KBS. And for the two different models, we see very different distributions. See a symbol may be blue in one model and red in the other. Then if we look at the same quantity when using the results from BaseLook, we see that these residuals calculated exactly the same data set, it's the same events, the same arrival times. But you see there's an absolutely beautiful, smooth change in this residual, which is essentially a correction to the applied velocity model. And you even see a couple of outliers up here and a few bright blue spots. And you can actually see in this plot that these are very, very likely to be outliers. Whereas in the plot to the left, where we'd located the events one by one, they're not outliers because these are quite typical. And we see that there's up to several seconds anomaly for some phases. And if we look at the next plot, we can also, just considering three different stations, either the first P arrival at the Hornston station and at Spitz, and then the S-wave arrival at Spitz. And we see that these distributions of travel time corrections that Baselock has come up with are changing from station to station. So the program is sort of implicitly calculating or calibrating the corrections that need to be applied to this velocity model to make the set of events fit with all the available data in all directions. So, and in this way, the group at Livermore in particular have been, most of their work on improving the 3D model structures done exactly in this way, by running Baselock and finding high quality solutions and then tracing back and finding out how the model is deficient. One of the key stations, seismic stations in this region, is the Spitz array. It's a very small aperture seismic array on Svalbard. A very powerful station for monitoring low magnitude events in the European Arctic. But it was understood very soon after the array came into operation in the early 1990s that the back azimuth, so the direction from which a wave came from, was very, very dependent upon the measurement you got for a given incoming wave was not particularly faithful to the actual direction. There was just a bias applied. So if you have an event which actually comes from 270 degrees, i.e. due west of the array, it actually comes, it looks as if it comes from much further south. And this is something that we need to calibrate for or account for when we locate events. And this was understood very, very early on. It applies to very many seismic arrays. And so then we bring on board one of these, what I call stamp collecting methods or pattern recognitions. And this is what we call empirical match field processing, where we just simply take the first P arrival across this array. And we see in this plot the estimate of the direction of arrival at the array that we would get by doing classical frequency wave number analysis. It looks to come down from this direction. But by taking the event locations that we already have and simply comparing the phase shifts over this seismic array with the phase shifts recorded for every previous event, it's very clear that the actual direction of the incoming wave is from a different place. And so in this way, we can probably further improve event locations, those that use directional estimates on seismic arrays. You see, take another view of the previous plot where you have the azimuthal estimation as a function of the back azimuth. When we do the purely empirical measurements, there's still quite a bit of a spread, and this is due to the fact it's a small aperture array, so the resolution is somewhat limited. But the bias is gone, and this is very important in sort of making high quality estimates with a very limited number of regional phases, which will be the case for smaller seismic events. Okay, moving to Central Asia, and the October 8, 2005 Kashmir earthquake was one of the most horrific earthquakes I remember from the start of my career in seismology. And I made a big issue of studying the sequence as well as I could. And the available event bulletins confused me quite a bit. I mean, we had the regional event bulletin and the bulletin at the International Seismological Centre also, We see lots of sort of spots in the top of the plot. And these are, for example, single array locations provided by the Kazakhstan National Data Center. So there's very different conditions associated with the locations of each of these. But there was a lot of data from regional stations which wasn't included in any of these bulletins, and I wanted to understand how much we could improve the locations by exploiting these. For example, if you look for the Nilor station, and it doesn't appear in either of these bulletins, whereas it's by far the closest to the open stations at the time. This earthquake was unfortunate with respect to the available sort of open seismic data. On the left, we see what the IMS looked like in 2005. So a lot of key stations that we take for granted now weren't in operation. On the right, we see basically every bit of data I've been able to get my hands on for this sequence. So IRIS have a wonderful data repository which has a lot of stuff here, and there were, for example, what's called the Manas profile, which had absolutely incredible signals from these events. Of course, the azimuthal coverage and the spatial coverage provided by these networks was very unfortunate with respect to this particular sequence. So I wanted to try and find a way in which we could exploit all the seismic data available without introducing bias, if at all possible. So we devised a system to basically take every single station which had recorded this sequence well and optimize the seismic traces for arrivals from events at this site. And we see these sort of characteristic traces, seismograms, and the paper which came out earlier this year sort of explains how we sort and automatically characterize all of these arrivals. And giving the output to the baselock program was an absolute revelation. I did several different attempts. These two huge clouds, which we see in the existing bulletin, sort of resolve into very nice structures with very, very fine dividing lines, and sort of as a strand going off from the middle into the Kashmir Basin and another strand up here. It's a completely different sort of spatial image that we get when we reanalyze the data in a way which the deviations from the applied velocity models can be incorporated. And we see here, just to emphasize the problems with this huge quantity of regional data with quite anomalous travel times. We're talking several seconds travel time anomaly from the AK135 model. If you apply the static corrections which you get out from baselock, you see a very much more sharply defined epicenter estimate. And if you don't apply these corrections, if you just throw in all the data together, then the estimate ends up 30 or 40 kilometers away. And these are big events in the over magnitude 5, so we should be able to locate these well. Now, apologize to all people who are part of the End Rainbow movement. I'm afraid I made this plot before that movement really took place, so you'll have to bear with me. And in the same way that I wanted to post-evaluate all the ridge events by calculating travel time residuals, I just wanted to try to get validation of the relocations for these aftershock events simply by calculating the differences in the travel time between a station to the north and the station to the south. And I think you should probably see a much healthier looking rainbow on your left than on your right, which sort of gives me confidence in the solutions obtained. And the same by finding CMT, global CMT solutions, so focal mechanisms for those events for which they're available. You see what the relocation vectors look like. They're quite significant. And on the relocations, you see that events with similar focal mechanisms, they do seem to cluster very nicely. And this is entirely sort of independent solutions, and these are just put in place afterwards. You see a couple of events that look like they have sort of strike slip properties. They end up in one place. Whether it's real or not, I don't know, but it gives us confidence, I think. Okay, on to another situation which unfortunately has been in the news a lot recently, is the North Korean nuclear test site. So why are we particularly interested in accurate event locations at the North Korean nuclear test site? And the reason is largely because the events take place in very steep mountainous terrain. And so accurate relative event locations will help us to locate these accurately in absolute terms, and give us some degree of control over the overburden, the depth, which will have consequences for how we estimate the yield. If you can imagine the North Korean nuclear test site being in a desert where it was all flat and all in boreholes, it would probably be of purely academic interest as to the relative location estimates. But it's quite significant if we move an event 300 or 400 meters in any one direction, just because that has a huge influence on the potential overburden. So it does matter. Now, the second declared North Korean nuclear test happened in May 2009. And of course, seismologists were very quick to jump on this and to try to locate event number 2 relative to event number 1. And this location here, using this network in Japan and South Korea and China, was published by Wen and Long in Seismological Research Letters in 2010. And they got a distance of about 2.5 kilometers. At the same time, Neil Selby from AW Blacknest in the UK, he did a similar location estimate using only a small number of IMS seismic array stations. And he got a distance of 1.8 kilometers in a sort of similar direction. And I told people I'm not happy with this, they should be the same. And people say, well, isn't it close enough? Isn't it good enough? But as the tests continued in 2013 and January 2016, the pattern was absolutely consistent every single time, that if you used stations in Japan or South Korea or China, you would get a much longer distance than if you used a teleseismic network. And so I wanted to get to the bottom of it. Now, on the left-hand side of this image, we see the North Korean nuclear test site in relation to all the seismic stations at the IMS. And then to the right, we see what we call the slowness projection. If you imagine yourself standing on top of the North Korean nuclear test site, which is not a place I want to be, looking north, what you see is sort of the view looking down into the earth, and where you see your continent is where is sort of the direction, the speed at which the wave you're at will travel. So you can probably see the United States and Canada sort of inverted here, in Greenland, and Europe back to front, and Africa and Australia upside down. So it's a kind of reverse image. So vertically down, the wave just goes down vertically, but at all these other angles, you see the direct teleseismic P phase. And further around at the outside is, of course, all the regional phases, which are traveling much slower across the slower apparent velocity, going to Japan and China, etc. And this so-called slowness map is of huge significance when we're doing double difference kinds of locations, because this is essentially a model telling us how far our wavefront has traveled in a given time. So when we make a differential time measurement, this is essentially telling us the distance supposed. And what we know is that this map of how the wavefront should be leaving the test site can't be right. And we know it can't be right exactly, because if it was, then the two images in the previous slide would be identical. And they're not identical, and they are consistently and demonstrably not identical. So what this is saying, in other words, is that each of these predicted slownesses is not quite right. There's a slight adjustment that needs to be made to the speed and direction in which the wavefront leaves the test site to reach these places. And we came up doing multiple inversions and searching absolutely tiny sort of time measurements. We came up with a set of what we call slowness correction factors. We simplified the model to assume that the wavefront was leaving in the same direction, but probably at a different angle of incidence, so with a different apparent velocity. And here we're looking from north to east, south, west, and north again. The red symbols are regional phases using the inversion, and the blue symbols are teleseismic. So here we see Japan and Australia down here, and then there's Eurasia, North America over here. And what's this essentially saying? That on one half of the test site, on the southern side, if you slow the waves leaving down somewhat, or more likely change the angle at which they're leaving the test site, and looking north towards Europe and Central Asia, they're probably going slightly faster than you think they are. This is the model which better explains the double difference time measurements anyway. And we can see by sort of imposing these sort of adjustments to the apparent velocities for the wavefronts leaving the array, that the preferred position moves a bit towards, and I have a lot more confidence in this position than this position, simply because the residuals are smaller and it becomes far more robust to the set of stations you use to solve it. And sadly, the North Koreans are doing more explosions faster than I'm able to update the plot. So this is the one that I did shortly after January 2016, which time there'd been only 4 explosions. And keeping the explosion in May 2009 fixed, I wanted to locate each of the other explosions relative to this test using different data sets. And we're essentially reproducing the results of Wen and Long and Selby. This is the Wen and Long results. I'm using only stations in regional distances. And it ends up significantly further, so 800-900 meters further away than if you use teleseismic only. But then when you apply these slowness corrections, the changes to the apparent velocity for the waveform leading, they almost fall on top of each other, and it's becoming much more robust. But in what sense does this make sense? Is it sensible to think that this is actually happening at the test site? And I would argue from the perspective of an array seismologist, well, yes, it is. We see this very, very often. And this is for the Spitz array that we were looking at in the first example. If you have a P wave arriving from an event at a regional distance due south, it will arrive with an apparent velocity of between 4 and 5.5 kilometers per second, which is very, very slow relative to the assumed upper mantle velocity. And yet, if you have an event from the same distance from the northwest, it's arriving with 15 to 20 kilometers per second. It looks like it's a teleseismic phase. And it was demonstrated in the late 1960s that if you simply put a dipping layer under a seismic array, you will see this kind of sinusoidal behavior with both azimuthal and slowness deviations. And we've observed this for almost every seismic array on Earth to greater and lesser degrees. So I think it's kind of obvious that we should anticipate a similar kind of behavior if we're performing so double difference type locations. You would never want to locate an event near to Svalbard using a back azimuth and slowness estimate from the Spitz array without performing this correction. And if you're unhappy doing that, you should be equally unhappy doing a double difference calculation of the North Korean tests using a layered model. It's exactly the same that applies. Now, in the late 1960s and 70s, there was this absolutely fantastic array in Montana called NORSAR, the Large Aperture Seismic Array. Unfortunately, it was taken away in 1978, although if anybody who uses the IRIS DMC, they will know a station called LAO in the US network, and that's the middle of this array, which has been reinstated. But NORSAR was a fantastic array just because we had lots of small aperture arrays right next to each other. And these arrays give us a very good idea of how the wavefront changes over the array. I'm very happy to Paul Earle, who's now with the USGS, because he read lots and lots of tapes from the NORSAR array for his PhD about 20 years ago, I guess, and put them out for the world to share, which I'm eternally grateful for. And here we see wavefronts on these two central subarrays of the NORSAR array from the Aleutian chains. So we see on this sort of slowness grid the point at which the model says that the wavefront will come from. But if we perform FK analysis and we measure the back azimuth and the velocity from which this wavefront approaches using the A0 subarray, it comes much slower than expected at almost the same back azimuth. And if you take the B2 subarray, which is only a few kilometers away, you see a significant sort of off-azimuth error, and it's actually going considerably faster. And just by considering lots and lots of earthquakes from the same region, you see that on these two subarrays of NORSAR, they're absolutely consistent patterns, but there's no way we can know this without measuring it empirically. And I think we need to have in mind that the same may apply to the source regions. From a purely scientific point of view, the North Koreans have been very kind to us in providing multiple events. And with 5 explosions having taken place, this is essentially a seismic array, but it's a source array. And the problem of event location and timing is essentially the situation that you have deployed a seismic array out in the field, but you didn't note where your instruments were, and the timing on each of the instruments is consistently wrong. But on the other hand, this very badly deployed array has recorded several hundred perfectly located and timed earthquakes. So this is kind of a reciprocal problem. So the problem is, okay, where are my sensors, or where are my explosions? And we can solve this as a sort of classical array processing problems using the time intervals. On the left-hand side, the grey symbols there are the sort of my favourite locations for the first 5 events that we get using these slowness corrections. And I've now thrown away the slowness models and the corrections, and I would say, okay, where should we place these events to optimize the plane wavefront for each of the receivers? And I fixed the apparent velocity to exactly as AK135 says it should be. And this is what happens. It throws them out again. So you have this 2006 event, again ends up 2.5 kilometers away. But if you then iterate and change the rate of change of time with each of these gradients, such that you always, instead of enforcing the slowness according to the model, you are solving for the slowness which best fits the arrival times, you end up almost back where we started from. And this calculation is not making any assumptions about the velocity structure. It's simply making assumptions about a common wavefront. And you can actually, by sort of considering this source array and classical array processing, you can actually measure the slowness at which the wavefront appears to be leading. And sure enough, you see for Matsushiro in Japan and Alice Springs, it seems to be leaving the test site slower than we think it would be. So this is kind of the last slide in a sense. This is kind of the image I'd like to leave with you of seismic wavefronts approaching an array, but could equally be leaving a set of seismic events which we want to locate. And we know the directions and the speeds at which these wavefronts ought to be leaving the test site or arriving at the array, but we know from years of seismic array observations that the truth is a lot more complicated because there's a lot of structure right at the source, and I think we need to start probably rethinking the double difference kind of methods with this in mind as a sort of, and I think the probabilistic approach we saw with base lock is probably a good place. It's just a summary. Our knowledge of Earth structure is getting better all the time, but it's not going to be perfect. There's not seismic data every place we want. There are not events everywhere we want. I think we can significantly improve seismic event location estimates without necessarily needing to improve the velocity greatly if we're able to account for and mitigate the biases. There are many different, I mean, base lock is the tool I've used, and this is the SSST algorithm, which, and if anyone wants a good master's thesis program, I'd love to see the same set of earthquakes and recordings being analysed both with base lock and the SSST algorithm, because I think they're essentially doing the same thing. They're calculating implicit corrections to the applied velocity model. So I would hope that it would give essentially the same results, and if they don't, it might give us a clue as to the performance or the applicability of the algorithms. So I think I've had very good experience using the probabilistic algorithms for covering regions of the world where we have difficulty in predicting travel times, particularly if we're a long way from the events, like on the mid-Atlantic ridge, or with very complicated structure and very poor station distribution as within Kashmir. And I want to think a little bit of caution with the double difference type. Can we validate all of the estimates we make with different kinds of measurements and try and build a more complete picture of the accurate relative location estimates? I think I'm done.
Well, great. Thank you so much, Steve. That was wonderful.
Okay,
Thank
thank
you
you.
so much for working through your cold. Um, so, as people are writing their questions into the question control panel, um, I just had a question to follow up about the North Korea events, mainly because I know that you talked like that these events seem to be happening so frequent with relative frequency that you haven't been able to update those plots. But I know that you had mentioned that this last event was particularly problematic to locate. Could you explain the reasons why that's been the case? Are you trying to go back, Steve, and you're are you having trouble, Steve? That I'm trying to figure out. Thanks, Bill. So Bill asked if we lost the phone call. I'm not sure because it's all been through the web, so we might just be stuck on the web. But also, if you have any questions as we're working on the technical difficulties, please feel free to write them in because I can, at the worst case, print off an Excel spreadsheet for him that he'll be able to get in contact with you directly to answer your questions. So please don't hesitate to let me know. So we'll hold on for another minute, and if it loses out, then I guess we'll be done. And sorry that we won't be able to have a Q&A period. Steve, I can still kind of hear you, but can you hear us? I guess maybe there's issues. Winter, I see your question, and I'll make sure that he gets it. And so Winter just had a question about the depth constraints on the previous slides related to Kashmir. So yeah, so I'll make sure that that question gets sent. Can you hear me better?
Can you hear me?
Yes, I can. Can you hear me? Okay, so what I'm going to do is I'm going to copy and paste questions so that we can hear you.
Can you hear me now?
Yes, can you hear me?
Oh gosh, you're back. I'm so sorry.
No, it's
Oh
okay.
gosh.
Technical difficulties happen.
Oh
Um,
god.
so I just put it in the chat box, but Winter asked, he or she says, "Hi, Stephen. I just went to comment on the depth constraint on your previous slides about the Kashmir earthquake, especially with so few stations nearby. So
Yeah,
could you
the
comment on that?"
depth constraint on these events is really terrible. I mean, I'm very interested in the depths that appear to be coming out from base look are quite consistent, but I don't know if they're real or not. So I mean, I don't think any of the constraints are good enough to convince me. I mean, the perfect thing would, of course, be to find teleseismic depth phases if we could do that at any distant array station. So if anyone fancies looking for them, I'd love to hear from you.
Great. I don't know if you heard my initial question about the North Korea.
Sorry.
I know it's okay. Technical difficulties happen. Um, about the latest North Korea event, I remember in conversation with you that you had mentioned that that event was particularly difficult to locate. And I just was hoping maybe you could talk about the reasons why.
the the signals generated by the most recent event were very much larger, a lot more low frequency energy than we saw in the previous events. And if you align the event signals in the dominant frequency bands, the signals from the new one event don't actually align that well, and there's quite a big uncertainty in the. We know that it's essentially happening under the peak of Mount Mountap, and all the different calculations we're running put it around in a similar location to the 2009, September 2016 events. But it's a more difficult calculation. Of course, the lower the frequency content of the signal, the more difficult it is, the less significant or the greater the uncertainty in the differential time measurement there is. So I'll be interested at the next conference to see what people have come up with.
Great,
For
great.
that one.
Right. Amy asks, regarding the Kashmir earthquake, do you think your locations would change slash improve much if you had data from India and or Tibet?
It would improve spectacularly. I mean, the Nilore station in Pakistan is superb. I mean, it's clipped for the largest of the events, but the Nilore stations is about 1 degree from the aftershock sequence, and the next closest station we have is 600 kilometers away. In one of the most unfortunate bits of timing is that these wonderful stations in Tajikistan, they came online about 3 weeks after the main event, which was a tragedy. So they've recorded some of the aftershocks, but if there's any way possible I could get hold of data from Pakistan or Kashmir or northern India, it would transform this problem. I mean, it would be a game changer. So I've shown what we can do with data from teleseismic and several hundred kilometers away, but it would be a game change to have local data. But I've been told by many sources that I should not have high hopes.
Okay, sounds great. All right. Well, that was just a couple of the questions that came through, and so we're getting kind of close to time anyway. So thank you so much, Steve, for your presentation. And if anybody has any additional questions, as they're thinking about it at home tonight or the day, please feel free to email them to me at webinar@iris.edu, and I can make sure that they are given to Steve. And thank you for everyone for attending and dealing with the technical difficulties.
I'm so sorry about that.
No, it's okay. And this always happens as I'm closing. A couple more questions have come through. One is just thank you, and that Bill Harbert just hopes that you feel better, and that it was a really interesting presentation. And Pen Chang asks, in single event relocation, how to correct the time delay introduced by the elevation contrasts of stations.
Are we thinking of North Korea here, I guess, or I mean, with the base lock kind of solutions, the elevation of the stations, the corrections is sort of automatically incorporated into the time offset. No, it shouldn't make any difference actually for either of the cases here. It should be. I'll correct myself if I think I've made a mistake here, but I think it's corrected for implicitly in the formulation of the problem.
Okay, great. All right. Well, with that, we all hope that you feel better, and have a great evening. Since it's 9.
Thank you very much.
And thank you so much, Steve, for providing this presentation for us. And again, it's recorded, so share it with your friends. It'll be on YouTube by the end of the day. So, well, thanks so much. Yeah. All right. Take care, everyone. Bye.
Cheers. Bye-bye.